So I'm very happy to have Anami with us. Anami comes from ICN2 in Barcelona, where I had the privilege of spending 6 months last year. We started the collaboration between RMIT and ICN2, RMIT and ICN2, because we were doing quite a lot of work with Siesta, which ICN2 developed. And we're also doing quite a lot of work looking at how we can try and predict inhibitor performance. The idea was if we could know enough about the attributes of a molecule and find out what ones were critical, we could then search molecular databases for molecules that have the critical attributes and then cut down the searching and experimentation dramatically. This is because we need to replace toxic corrosion inhibitors with non-toxic ones. That's been the idea for about 15 years. It hasn't really worked that well. And one of the reasons it hasn't worked that well is because our models have been too simplistic and we haven't been able to model quite a lot of the chemistry and electrochemistry that happens, and therefore our development of molecular attributes to do machine learning hasn't been accurate. Realizing this probably now about 4 years ago, we formed a partnership with ICN2 because not only are they extremely good molecular modelers, they also extremely good code writers, and they had written a new code called Siesta that allows the incorporation of both solvent effects and potential effects. And Anani has been pioneering the application of that to inhibitors along the way, solving various code and programming issues. And so this obviously is terribly important for my team's work, but it's also generally important in how you model molecules and surface interactions. And as I was joking with Gary, this is the logical conclusion of 150 years of metal bashing. So can we actually fully design the system virtually before we go and try to make it practical? So with that, I will pass over to Anani.
Okay.
Spend about 35 minutes and leave us about 15 or 24 questions at the end.
Perfect. Okay. So hi, everybody again. So I already introduced myself. I am a postdoctoral researcher there in ICN2. Before I start, I'd like to thank you all online and you here for listening. And of course, Ivan, for giving this opportunity. So it's been a while since I started to collaborate with Ivan, and we were planning this visit, but I mean, it was never possible to come, but now it worked, and I am happy to bring some of the results we obtained in the last years working with Ivan. So the title is Electrochemical Molecular Modeling from Green's Functions to Hybrid Quantum Mechanics, Molecular Mechanics. So I want to show you the fundamentals of this method that is implemented in the Siesta code, and also some of the results that myself and the PhD students we share have obtained. So this work is led by Pablo Ordejon in Spain and Ivan Cole here, and several PhD students are involved. So Jose Maria Castillo, who is here on the audience, is our most senior student. And we also have Maza Iqbal, Michael Morgan, Paul Fabre, and Sara. The first 3 we share between the Autonomous University of Barcelona and RMIT University. And some postdocs, Stefano Picardo from RMIT Europe, Federico and Gabriela from ICN2. Before I start, I'd like to show you where we are actually. So we are in Barcelona city that you might know by this beautiful church here, the Church of the Holy Family, Sagrada Familia. So next to this church, we have RMIT Europe, which is a hub of the RMIT University in this building here, sharing space with some industries. So it's a very nice location. And next to here, there are some nice beaches, not as nice as those you have here for sure, but it's a nice place to work. So in this is Barcelona city. So crossing a small mountain with some a small forest here, we have the Autonomous University of Barcelona campus. which is here. And inside this campus, we have this little green building here, where is the Catalan Institute of Nanoscience and Nanotechnology. So there we are, and Ivan spent 6 months with us, going to this place every week. So it was very nice to have him there. So why we study electrochemistry? So I'd like to start with this because we are interested in the corrosion problem, which is the expertise of Ivan here, mostly doing experiments, but he's also doing continuum modeling, as I explained. So I don't want to enter into many details why this is important, because you probably know that very well, since many no faces are here. So the thing is that this is a complex problem where we have metal being corroded by the environment, and that generates electrified interface. So we have cathodic area, anodic area, many chemical reactions taking place. And if you wanna do molecular modeling on these things here, there are 2 factors that are key. So to include the solvent effects and to account for the electrified interface. So this is what we can do now in this method that was developed, and I want to show you some details of that. But before going into details, why modeling electrochemistry and why this can help us? Because from the experimental point of view, there is plenty of research, and why the modeling can help. So using computer simulations, we basically write several algorithms and computational codes that can, for example, help us in understand how covering a given metal with specific molecules will prevent this metal from corroding. And we can test several molecules, and we can basically have an atomistic resolution here. So if we change a single atom, if we change the molecular orientation, if we apply a voltage, if we consider the solvent, what is going to happen? Well, this has several advantages and disadvantages that I want to share with you, but I will start with the disadvantages to not be biased. So sometimes, actually, many times we present unrealistic models, as Ivan was saying. So we need to go beyond these unrealistic models and to provide more realistic simulations. What is realistic simulations? That reproduces better the experimental conditions in the real world. And we are sometimes slower than experiments, but once we develop the method and we test it, then we can be often faster. We don't use chemicals. We can separate into degrees of freedom, so understand each phenomenon at a time and down to under atomic resolution. So these things combined with experiment can be very promising in this area and help us in understanding what are the properties a molecule must have to behave to be a good corrosion inhibitor. Well, there are many different types of simulations. So here I bring to you a time scale above here and a size, a length scale down here. So starting from the modeling that does the largest scale in this slide here, we have the continuous simulations, basically solving partial different equations, which are in the seconds or millimeter scale, which is the expertise of our colleague Milan, and they do this here in the RMIT University in Ivan's group. So if we decrease this scale, we reach the microsecond scale or the micrometers, where we have some mesoscopic simulations, such as Monte Carlo methods. If we keep decreasing these, we reach the nanoscale, nanoseconds and nanometers, where the most common methods could be the molecular mechanic based ones, which, for example, we can select here the classical molecular dynamics. We can then keep decreasing these and get more resolution and understand the role played by the electrons using quantum mechanics, mostly density functional theory. This is the most popular method in this area. So then we reach the femtosecond scale and angstrom length scale. And of course, we can understand how electrons take part in chemical reactions and how they take part in this phenomenon in electrochemistry. In our group there in Barcelona, we are particularly interested in the overlap between these 2 scales here, where we combine quantum mechanics and molecular mechanics. This is called QM-MM method. Why that is a nice approach? So we combine the accuracy and the predictability of quantum mechanics, but very expensive calculations, with the very cheap, albeit less accurate and less predictive molecular mechanics. So we combine the best of each world, then we can go to larger time scale and to larger length scales. So this is basically what we are doing there, and I will bring you some details here. Before I enter into details of the method, so how this all started. So how we consider water molecules in the simulations at the same time that we consider the electrified interfaces. So we, as always, started with very small systems and then increased it onto the point we are now. So first thing was in 2018. This was not in our group. It's a work done by Pedrosa et al. So she investigated the interaction between a single water molecule and electrified interfaces. That was the first work that we extended in our group back in 2021, where we included 40 water molecules in the electrified interfaces. We then increasing this even more to liquid water. That is the part where I started to collaborate in the group, so that the first results came last year, the first important results. And our next step will be to consider electrolytes in the solution. We are still not considering, but it is on the horizon. In terms of the PhD students involved here, in 2021, Paul Fabre is a PhD student in the group. He obtained the first results. In this part here, we have Jose Maria, who is in the audience, Maza Iqbal, and Mike Morgan. Those three are shared students between RMIT and UAB in Spain. And as for the electrolyte, a new PhD student started recently there in I-22, and she is developing a code to account for the electrolytes, as I showed to you in the last slide of this presentation. In this presentation, I am going to focus on what the results we have obtained, so myself and the PhD students, mostly the PhD students, and on the perspectives about including the electrolyte. So what is our final objective? What is the model that we would like to have in the end? We would like to go beyond the standard EFT, account for the solvent, and account for the electrified interface. So the systems we have are like this. We have a metallic slab on one side, another metallic slab in the other side. We have one of these surfaces covered by corrosion inhibitors, a self-assembled monolayer, and we have the solvent in between these two sides. And the thing is that we apply a voltage, so we connect this to a battery, and then we can keep each side under a different chemical potential. I'll give some more details on that. After making these, we can extract some properties at these interfaces that are, for example, we can understand how the inhibitors will displace the water molecules from the interface and then forming a physical barrier from the corrosive media. If we want to do these things, there are three key factors. Two of those I already mentioned. So we need to account for the solvent here. We need to account for the voltage applied, and we need molecular dynamics because we are including water molecules. So water molecules requires molecular dynamics to have a equilibrated sampling of the system. So how we do that? As for the voltage, we include the voltage considering the non-equilibrium Green's function formalism. This is this acronym here. It is implemented in the trans-siesta code. It's a module of the siesta code. So it's a functionality of the siesta code. It is a method that is developed, it's proposed since a while, but some 5 years ago, it was revamped, and it allows us now to do molecular dynamics, ab initio molecular dynamics with a voltage applied to the electrodes. What is the main fundament? What is the main fundamental here? So we have two electrodes, two semi-infinite metallic electrodes, one in the left, one in the right. So the system is infinite in the direction of the electrodes and is finite in this central area here. We split the system into the left electrode here, the right electrode here, and in the center, we have the simulation cell. And what we put here is what's gonna interact with electrified interfaces. We can have, for example, inhibitor molecules and understand how these inhibitors will change the interaction with the surface that are now electrified. So this is how we can go beyond the standard EFT. Or we can have water molecules or any solvent in between and understand how this liquid responds to the voltage we apply to the electrode. The main thing is that we shift the chemical potentials. In the left side, we shift upwards, and the right side downwards, and then we can run simulations under a voltage applied. So this works well, but even after this revamping, it is still computationally expensive to include liquid water. So we can go beyond that by considering this QMMM method. So what is the main thing here? We split the system into two regions. So we need to make a rational decision. So which part of the system we will see a quantum phenomena happening, and which part, the quantum part, is not that important. So we make a rational splitting here, and then we can apply this to electrochemistry. Why I mentioned that? Because it is usually applied to biophysics, so it's a well-established method in biophysics area, and now you are starting applying this to electrochemistry. In the context of electrochemistry, what we do? We have the central part that can have the liquid and the counter ions. We couple a source and a drain. We apply a voltage, and we treat each part with a different level of complexity. So the inner solvent here, the bulk solvent, which is far from the quantum part, it is treated with molecular mechanics, which is less expensive, more affordable. And the electrodes and anything we attach to them is treated through quantum mechanics. So that's basically the split we do to apply QMMM with the Green's functions. But how we couple the QMMM and the Green's functions? Well, the main equations are well known in this area of molecular modeling. So in the QMMM fashion, you split the Hamiltonian, so this is the main equation of the system, into three contributions: the Hamiltonian of the quantum part, the classical part, and the hybrid term. From that, you can compute the total energy. In this case, is the constant, the electronic energy, and then the classical energy and the energy of the hybrid system. The energy of the classical part is a basic force field energy, so that any classical code doing molecular dynamics can do. So you have bonds, angles, dihedrals, and some non-bonded terms here, which are Coulombic and van der Waals interactions. So that's like a standard. And then the interacting system, here in this equation, we interact the QM and MM atoms. So the green things here belongs to QM and the yellow to MM. So the electronic density, so how the electrons are distributed in the system, interact with the classical charge of the MM atoms. We also have interaction between nuclei and the dispersion term. After that, we have the classical potential being summed in the QM atom. So this equation, the left, it can be understood as the effect of the QM atoms on the MM ones. And this one here can be understood as the effect of the MM on the QM ones. And then this potential is a point charge potential that has a very simple shape. So this is the basics behind this QMM, which is very similar to any QMMM implementation. But how we couple this with Transiesta? First of all, if we look at this expression, here we have the electronic density from the quantum part. If I make a plot, just an illustrative plot of this electronic density, taking the difference between a case without a voltage and with a voltage, we can clearly see charge accumulation in one of the extremes and charge depletion in the other extreme. What that means? The effect of the voltage is already present in this term, and we interact this with classical charge, so the classical atoms will respond to this. But we need to account for this voltage in the classical atoms as well. So there, what we do, this ramp potential is what we do in Transiesta. So basically, considering the high and the low voltage and the size of your simulation cell, you can compute what is electric field generated. And then you can plot this ramp potential. If you check, considering 2 volts applied, you can check 3 regions of this ramp. So here, where Z is equal to 0, you would have the plus 1 volt, at the center 0 volts, and the other side minus 1 volt. It's the same thing I showed in the other slide. So what we need to do, we then add this electric field to the QM atom, sorry, to the MM atoms, because this is the expression of the MM atoms. So here we have the MM atoms interacting with the quantum atoms here, and they are also interacting with this electric field generated by the voltage we apply. So this is how we couple non-equilibrium Green's functions and quantum mechanics, molecular mechanics methods. And now I will start showing more nice things. So this boring part of equations is finished. So when we do QMMM, of course, we are losing a bit of the physics here. So we need to, again, performance. So the very first thing we can evaluate is how is the performance here. So can we really go beyond and run like longer molecular dynamics? To test this, I made some tests in a supercomputer in Barcelona using this amount of CPUs with this hybrid scheme, parallelization scheme, which is not, I'm not into in details, but if you want to know more details, I can explain it to you. So considering this gold electrode, so gold on one side, gold on the other side, in QM part, we increased the amount of classical water in the center. So this is an example of 3 units, let's say. So we have here 1, 2, and 3 units of water. So that is in total, 1 unit has 236 water molecules, and then we increase this into 10. That means in total number of atoms, nearly 8,000 atoms. And then we tested the performance of this in this architecture here. So we made, here I plot the wall time, so how much time the simulation takes as a function of the number of units, let's say. So from the case with 236 water molecules into 2,306 water molecules, total 8,000 atoms. If you see the results for everybody being QM, it increases a lot as we increase the size of the system, albeit it is remarkable that Siesta can still handle such a big amount of atoms. But if you do this with QMM, so in this case, we are increasing only the amount of MM atoms. That's basically costless. So we can have nearly the same cost as having like 10 times less water molecules. And if you split these contributions, you can see that the MM part is not representative. What that means, with QMMM, I can have 1 picosecond per day for this particular system. That means 1,000 steps. And if it was full QM, that is 10 times less. In terms of, for being more clear for you, let's say to have 30 picoseconds of simulation, it's enough to calibrate water. We need 1 month with the QMM. It's a lot, but it is affordable. If it's full QM, that means 10 times more 1 month, so 10 months. So we don't have so much time to wait for the results. We are anxious. So what are the results? Then I showed you that the method is performing well, but what are the results? I am starting with the results that I myself obtained. So here, just to prove that everything works as expected, we simulated a case with the gold electrodes in contact with water molecules. So here I am plotting just one side, and this is the case where the water interacts with a surface where I apply 1 volt here. So I can plot the density, the distribution as a function of the Z, so as we go far from the surface, of hydrogen and oxygen separated. We can clearly see both in the picture here that some hydrogen atoms point toward the surface, and we can see this small hydrogen peak here. So the water molecules are responding to the electrified interface as we would expect. We can also check this to confirm in terms of the angular distribution. So how is the water orientation because of the voltage we apply? We can evaluate these, splitting the water in some regions, like the left side, the right side, because they're different since I apply a voltage, so they charge differently. And then the bulk water here in the middle. So the 2 angles we can look at are the dipole angle. This one is the angle between the water dipole and the normal to the surface, so the orientation of the water. And the other is the plane angle. So is the water lying like parallel to the surface or perpendicular? So those are 2 angles that are nice to look at. If we evaluate this for the left top layer, bottom layer, in the bulk case, when we do not have a voltage, so both sides are similar, and they are different from the bulk because they are interacting with the interfaces. And then when we apply a voltage, we can clearly see that they are shifted. So that means that the water molecules, in average, they get aligned to the electric field that is generated here. So everything works very nice here. So from this plot and here, you can see that it is equilibrated. So we then applied this to corrosion. So that was when Jose Maria Carcillo started the PhD, and then he applied this to corrosion inhibition. But I forgot this slide here. So this one, here's another way of evaluating the interaction between water and gold. So we can see how is the charge on the electrodes along during the molecular dynamics. So for the same system, we can see that for positive voltages, this side becomes negatively charged, and then it attracts the hydrogen that are on that side. And the other side becomes positively charged. You can plot these charges here as a function of the simulation time. So if you see right electrode above and left electrode below, for the different voltages we apply, the surface gets charged. For example, the yellow curve here. So the charge fluctuates around -2 in this case. This is the sum of all the gold atoms. And here, -2, and here +2. In the case without a voltage, blue and red, the charge on each side fluctuates as expected because of the random distribution of water close to the interface. So this is showing that this method could be applied efficiently to corrosion inhibition. And now, yes, it's what Jose Maria did in the beginning of his PhD. So first thing he did was to evaluate the interaction between this molecule, which is a corrosion inhibitor for copper, with copper surface. So he made a adsorption site search. So he tested several different positions of this molecule above copper, and they also changed the coverage, so the amount of molecules and the shape of the box, to end up with a adsorption energy as a function of the coverage, like in this plot. So as we increase the coverage, we can clearly see that the adsorption energy decreases, so the system gets more stable. So the formation of a self-assembled monolayer is stabilizing the system here. Then what happens, because this is like DFT, no voltage, no water. What happens if we apply voltage here? So for these 3 adsorption cases, so 3 examples, here we see the difference between the voltage, the case at 1 volt and 0 volts, for 1 and -1 volt, 3 different adsorption sites. So we see that because of the voltage, there is charge accumulation at the molecule's tail here. And in the other side, everything behaves as expected because we don't have molecule there. So the application of the voltage leads to an accumulation of charge for this adsorption site here in the tail of the molecule. And here, since it is parallel, it is distributed in the molecule. If we take one example and look density of state, so how are the electrons distributed for each energy, we see that the lowest unoccupied and the highest occupied, they are close to the Fermi level. That's why the molecule can get charged and discharged because of the voltage. What are the implications of that? Since you can see that the voltage affects this part of the molecule, that can have implication in the formation of the second layer of inhibitor, because we know from the experiments that we can have a multi-layer of inhibitors. So this was nice, and then we moved to the case where we can account for the solvent. So now we have voltage. So let's see what happened to the solvent. So this is one example of simulations that Jose Maria did. In this case, we account for the water molecules in the system and a self-assembled monolayer fully covering the interface. This is just to show you how it works. So here we have the copper and the self-assembled monolayers and the water molecules. This is molecular dynamics that he did with this method, QMMM, coupled to the non-equilibrium Green's functions. What we can extract from here? If we go to this case here, Jose Maria selected 3 case systems. One is without the inhibitor molecule, this above one. The middle one is the case with a single inhibitor, that means low coverage. And the third one is the case with a self-assembled monolayer, so full coverage. And here in the left are the water distribution as a function of Z. Same kind of plot I showed before. So here you can see, first of all, the water is equilibrated at the bulk. And what we can see is that we have a structuring of water here that is strongly affected by the presence of the inhibitor. So going from one molecule to a full coverage, we see that there is no water molecule getting close to the surface, even in this case where actually the inhibitors, they could leave the surface if needed, because this is molecular dynamics. So the layer of inhibitors is stable and is protecting the metal from interacting with water. So we need to go beyond, is outside of the scope of his PhD, but we need to go beyond and consider counter ions. But Jose also included voltage here. I'm not bringing anything related to that. He's now finishing the thesis. Other kind of works we have been doing collaboration with Ivan's group. So is the case where this molecule MBT interacts with zinc surface. This was also in collaboration with Dr. Deng. He defended his thesis recently in Ivan's group. So here I bring this to show you how we couple the experiments and the modeling, how we can make these two words that looks too different to communicate to each other. So in the left, we have XPS measurements that Deng did. And in the right, we have molecular modeling that Jose Maria did. So with the XPS, you can compare the case of the molecule before you absorb it in the surface and also after absorption. And you can compare this with the molecular modeling. In the molecular modeling, what Jose Maria did was to check, for example, two different cases, self-assembled monolayers, where the nitrogen from the molecule is interacting with the surface and where the nitrogen is not directly interacting with the surface. Jose computed adsorption energies. This one is more stable, so it looks like this one will be predominant, the one with nitrogen pointing to the surface. How does that compare with XPS? Well, if you look the sulfur, you can see that the case not adsorbed and adsorbed, you don't see any shift here. That means that sulfur is not binding to the surface. If you check this sulfur here, yes, we do see a small shift. That means this sulfur is binding, and it is indeed in both adsorption cases, it binds to the surface. And for the nitrogen, we see that it is binding. So that means this case where nitrogen is pointing to the surface should be more favorable, and indeed it is. So we could corroborate the XPS measurements with density functional theory. Then I'm approaching the end of the presentation, and now I'm going to show you the next steps on this. So one of our PhD students, Maza Iqbal, he started 1 year ago. He passed his first his COC last week. And he is going to extend Jose Maria's work by considering an oxide layer of copper between the copper and the molecules. Why is that? So copper suffer natural oxidation. Then we need to account for this, because the interaction energy between these corrosion inhibitors will not be the same with the bare metal or with the oxide cases. Of course, Jose Maria started by the simpler cases, and now we are going beyond by considering this. He will apply this methodology we developed, but he'll also go beyond by considering not only the oxide layer, but also electrolytes present in the solution. So this is next step in terms of these systems. So here is the same case I showed before. You have a monolayer and a single molecule attached. And in this part here, we can consider an oxide film and see how that changes the findings that Jose Maria obtained. The other project we started recently is the alcohol. So this project here is something that it is different from the previous project, but the final objective is the same, protecting metals from corroding. In this case, the idea is to propose new rust-resistant coatings for steel. The steel is the material we are interested here. But we are not going to protect them with the inhibitors, but in this case, covering with recycled aluminum. So this recycled aluminum are alloys that are usually discarded, and we want to propose a use for this. So facilitating circularity and also proposing a good solution to prevent steel from corroding. That in principle can lead to superior performance. We propose it because of this, and promote circularity. This project is the one that Michael Morgan is involved in, and also Dr. Stefano, who is hearing us from Europe very early in the morning. Thanks for being here. And the final model we will have is something similar to this. This is a sketch, okay? So we will have the steel metal here in the atomistic simulation, covered by aluminum alloys. And in the final model, we will include the electrolyte, the solvent, and check how the potential drops across the several interfaces here. This is the molecular modeling part. There is a continuum modeling part, which will be developed by Stefano and guided by Ivan, where we aim at obtaining several molecular modeling attributes, parameters, like from energy, charge distribution, the potential, and try to feed continuum modeling simulations with those parameters. So that's the main purpose of my visit here. We have had some progress on this, a special thanks to Dr. Milan, helping a lot on this. So here we need to work a lot, basically in translation of the terminologies here, because the physicists and the electrochemists, they use different terminologies. So this is the main idea of this project. So concluding, in terms of including water molecules and considering for the voltage, so this is basically what we have been doing so far. And then next step is considering the electrolyte. So to consider the electrolyte, the models here will agree with me, we need way longer simulation times to equilibrate the ions. So that's not feasible with 1 picosecond per day. So our idea is to implement this method that was proposed many years ago inside Siesta to couple this with the QMMM. So the main idea is to do molecular mechanics on the electrodes. This is a good approach, albeit it cannot capture, for example, chemical reactions, but it could be used as an initial structure for us to then move back to QM or QMMM. So the idea is to use Gaussian charge. I'm not going to into the details. Then we use Lagrangian to evolve these charges, and that will generate a way faster sampling, which we can go back to QM or QMMM. This is currently being developed in ICN2 by Sara Navarro. With that, I'd like to thank you all for your attention, for being here. Ivan, thank you once again for this opportunity. Thank you, the Tier and Simulation group. So here we have the PhD students and the most of the postdocs, Pablo Ordejon, the group leader, and those are all the projects, the funding that are involved in everything that I presented here. Thank you very much for your attention.
Thanks very much for that. So I want to start with a couple of general questions and then we'll get into the technical questions. So I was saying to my old mate Gary, who is a very traditional methodologist of same old school as I am, that we'll be able to use these modeling techniques to replace doing the experiments. So how far away are we from using virtual models to replace the actual experiments?
Yeah, well, I don't think that we will end up replacing, but we will probably end up doing much less experiments, or at least like more specific experiments. So I think we will never like replace, but we are approaching the point of being able to consider every single ingredient that is required to have realistic models and to save a lot of time in the experiments. So I think we are approaching this, but it's hard to say how far we are.
Okay. Let's go to more questions from the audience then. Any questions from the audience? They can be technical, they can be general.
If you want to make some question, I can repeat it here to make it clear to the people online. There is a question from the online audience. Should I read this one? So I read it. So, hi, thank you for your presentation. My understanding is you are trying to expand the system, but is the simulation is at a specific point of the metal electrolyte interaction, or is it dynamic? I mean, over time of metal electrolytes interaction. I see. So this is, thank you for this question. And this is molecular dynamics. So the electrolytes, when they get close to the interface, they can interact with these electrified interfaces. So if your question is related like to chemical reactions, like cathode, canonic reactions occurring during the process, this is not possible to be captured here in this method, unless we change this partition between QM and MM. So for instance, we can have the things we want a quantum phenomena, so a chemical reaction to be studied, we can include in the QM part. So in what I showed, that's not possible, but it is possible to be included if you want to. If that was your question, if not, I can try to answer again. That was for Alsma. Yeah, so her question is about the size of the QM part, how big we could go. So to run efficient molecular dynamics so far, the biggest systems were the ones by Jose Maria that have around 300, 400 atoms. We can go beyond if we use more CPUs and we parallelize it better. So the group there, since they developed Siesta, they are constantly improving the efficiency of the code. So I truly believe that we can go like 1,000 atoms very soon in the QM part. That is for molecular dynamics. But another possibility that can also be used here is to sample everything with classical molecular dynamics, that it's actually many times very good to sample the structures. Then we select the snapshots and we go on to single point calculations over many snapshots. That sky's the limit for the size of QM, because I mean, CS is quite good on handling this. So since a single point, I mean, if you take some hours to be done, you do several single points at the same time. So it really depends. So I would say molecular mechanics from 400 to 1,000, molecular dynamics, sorry. And if you go on snapshots, even 8,000, 10,000 atoms could be in the QM part. Yeah. Yeah. Yeah, so now I just repeat because of then here, because the microphone is only here. Yeah, so the question is the vacuum distance, if that's enough to prevent them from interacting to each other. In the Green's functions formalism, they don't interact at all because we don't have PBC conditions in ZIT. So it's like they are infinite in X and Y, but in ZIT, they are not periodic. So the size of, if I increase the vacuum, that means, of course, if they are too close, we can have interactions between the two sides. But if we increase like some dozen, like 10 angstroms is already enough for the states to not overlap. But in this case, that we have liquid water in between, we are talking about something, if I'm not mistaken, 40 angstroms, right, Jose, of a space filled with water. That's enough to have bulk, like as we discussed the other day, that's enough to have bulk like water molecules. But we, for example, we can go to larger systems. If you want to have dilute counter ions, then we can increase even more and then decrease the concentration of counter ions. Yes, those are very interesting points. Thank you.
Other questions? Oh,
Hello, mate. So just being devil's advocate for a second. So within Maria has done the computational. In my experimental setup, I can do 80 different inputs in one experiment. How quickly would it take you to do this?
Yeah, so that's precisely the topic of our early meeting of next project that Ivan is involved. So how quickly we can obtain the results, like changing molecules, right? Well, in this case here, we were interested in getting a fundamental understanding and to test the methodology. But if you want to go like to scan for several molecules, we should go to other directions like the single point calculations and do sort of high throughput. So that means a lot of different molecules being attached one at a time and try to define an attribute we can look at. So this is possible. Actually in Siesta, there is a module, there is a functionality of doing this high throughput, but not molecular dynamics, because of course this will take months, but depend on the property you want to look. For example, let's consider that the adsorption energy will be an important attribute to look at. So this can be obtained like in one day for each molecule. So if you run like a lot of molecules at the same day, because you have supercomputers, then you can scan hundreds of molecules. So it's a matter of proposing a method for that and adapt to Siesta. It's quite possible.
That's like a slightly different question there. If you were to put two different individuals in at the same time, how would it handle that?
You mean the layers of inhibitors that are composed by more than one inhibitor?
Competing.
Competing inhibitors or synergistic inhibitors.
Like the two at the same time? I mean, in principle, that can be done, but I mean, we need to think like on concentrations, and we need to think on the, I mean, because usually if you compare the absorption of a single inhibitor isolated and the other one isolated, more or less you can see which one is interacting more strongly. But if you want to see the two at the same time competing, you need to think on a model for that. I mean, I don't see limitations to study this. It's a matter of thinking on the problem and proposing, in this case, the model.
Well, what we can't do yet is precipitation. We know some of the inhibitor couples work well because one is forming one away and the other is precipitating. We can't yet do the precipitation, although there's no intrinsic reason that we shouldn't be able to. We've got to build a bigger system and the possibility of interaction in the solvent, which we don't have yet.
Yeah.
Any more questions?
Thanks for your talk. I was wondering, how you want to tackle the problem if you're not with MD, so MM gets more complexity, and you have different species of atoms or different actions, like in the alloy, you have element A, B, C. How do you want to actually parameterize predictably your MM?
Yes, that part, that's a very nice question. Thank you. About parameterizing the MM in the case of a very different systems like an alloy. So for that specific project, we are not planning MM. So the alloys and everything will be in the QM part. So the MM will be the liquid, which is well parameterized and well known. So we will propose the microstructure of the alloys using quantum mechanics, which is predictive. So we don't need to care about parameterizing. But if we would like to go on the MM side, then we would need to parameterize, and that's not precisely my area, but I think that could be possible as well. Once you have the structure, you can use, for example, the FT to parameterize the MM. Yeah. But in the specific case of this project, the alcohol alloys will be QM.
So I want to, this is sort of a Dolby Dixon, but I want you to, one of the advantages of the modeling is to get a more fundamental understanding. So I guess between your work and Anadi's work, what your understanding have you got that would excite an electrochemist that you didn't have before you started?
Okay, so maybe I think that the most interesting result so far is that we can demonstrate that indeed this inhibitor film is stable over time, even when we apply different voltages. So indeed, the water cannot get close to the surface when it is fully covered. Another interesting result is the charging and discharging of the molecules. So I think that so far we were not expecting that upon a voltage that the tail of the molecule will be charged, and that will for sure will have several implications in the multiple layers, which is the next step. So I think that the fundamental understanding, atomic understanding on the multiple layers is will be something very exciting for the electrochemists. So I would say those two things so far, but more results are coming from Jose Maria's post-processing. And yeah.
I certainly agree with you in the second. We expect the traditional model of inhibitors to both blocks the water and acts as a challenge barrier. But as a normal electrochemist, we always knew it was blocking the water.
Yeah.
So that's not startling to us. But this charge rearrangement, formation of a dipole, we have not seen before. So that is new to us. It's very new.
Yeah. There is another question here.
Good.
Like a follow-up question. So this person that asked it before is saying that he or she is referring to the snapshot. If this is a snapshot in the inhibitor performance, but in his understanding, it is the performance of the inhibitor changes over time. Yeah. So I think now I got the question. So in the time scale we are simulating here, we are in the time scale of picoseconds. So that is basically nothing for the time scale of the duration or how like we cannot see how stable the film is over time in terms of corrosion inhibition performance. Okay, so this is like the very beginning, but if you want to go to longer scales, we can do classical MD and extract structures from there, and then we can reach nanoseconds, so some hundreds of nanoseconds in an easy way. So if you want to keep discussing this, you can send me an email, and then we can talk more about this.
Okay, let's go to the people online. Gary, do you have any questions as an old metallurgist like me?
No, I thought the presentation and the work's very fascinating. In my mind, doing some sort of metaphor, I was seeing of the moat being tweaked to preserve the castle, and yeah, ready to see how it all develops. Thank you for the presentation.
Welcome.
Navina, do you have any questions?
No questions from me. Excellent presentation, Hernando. Thank you very much.
Thank you very much.
So, Dan, as a experimentalist, what is your thought about this? What do you see any value, or as Paul implied, we just do my experiments quicker? Dan, I don't know if you tried to speak to us, but you're muted at the moment.
Oh, I'm sorry, it's muted. It's a very nice presentation, Anthony. Yeah, I think Paul got the point. Like, modeling can be quite powerful technique. Like, in terms of how we can combine the modeling technique with the environmental results, and to explain like what we observed from the experimental part will be something we should expect, and something we should look deeper.
Yeah.
Okay, so
Yeah, like for the time being, like say we from our knowledge, we know certain modes of absorption behavior of inhibitor molecules. Like how can we like represent those movement or those chemical reactions, like using modeling technique can help us explain more in depth what's really going on, and in turn will help us to understand better like how inhibitor works on a metal surface. Yep.
Yeah.
Okay.
Thank you.
Stefano, it's too early in the morning, you're probably still asleep, but any questions or comments?
Sorry, I was muted. No, very interesting meeting. Was very useful for me to better understand of the molecular and atomic dynamics underneath. And so thank you very much, Hernani.
You're very welcome.
Okay, then, we have about 3 minutes left, so any last questions from the audience? Paul?
Yeah, one more. So, if you show that the inhibitor absorbance and stop the one in practice, a lot of the organic inhibitors, when you change the concentration, as in remove the inhibitor from the solution, like the salt solution, stop working because the inhibitor gets knocked out of the surface. With the model, could you explain it in this way? Why?
Maybe also connected to what we discussed earlier today. So yeah, very interesting point. So Paul is asking about that the molecule sometimes it stops to work because it doesn't bind to the surface. So in this sense, one thing that could be done here is to study the kinetics of this. So for example, what is the energy barrier that need to be overcome for the molecule to come from the bulk solvent to the surface? And based on this, we can make some estimations on if it will be possible, if the other way will be more favorable. So with what I presented, we cannot say nothing about this, but there is a possibility of doing this, and maybe we will share another student exploring this part now.
One of the things that ICM2 and others are working on is a snapshot approach, because you can only have a model a tiny amount of time. But can you understand the fields enough so that we just take snapshots in time and understand what conditions happen at a certain time? So we know that randomly there will be electrochemical activity occur, which may then reduce surface charge. So can we take some time in the future and say what happens if there's some surface charge, for example?
Yeah.
Or like you said, just take some time in the future when there was no inhibitor solution and see what happens there. So we will investigate. We can't really do time, but we can do snapshots and change the condition at each snapshot and see how the system responds. Okay, so we have now reached the time. So thank you everybody for attending. Thank you very much, Anani, for presenting. Thank you to Materials Australia, the Computational Network, and the Electrochemical Network for your sponsorship. Anani will stay for a few minutes, I'm sure. If anybody has any questions, I'm going to ask you to.